Okay, let's begin. I'd like to welcome you all to this afternoon's workshop on turbulence. Our chair has just arrived. He's also our first speaker, Katepalli Sreenivasan from NYU. Srini needs no introduction. Of course, he's a leading figure in theoretical, numerical, experimental aspects of turbulence. So, Srini, if you're ready, I'll now let you take over.
Thank you, Tom. Now I have to find my talk.
I will mute myself.
Okay, I'll share my screen in just a second.
Yeah, it's a button down there.
Yes, share screen. And I think this may be it. Okay, very good. All right. Sasha, can you see my screen?
Yes, I can.
Okay, good. So now I can start. So I am really the person who introduces the next two talks, more or less. And so what I say is very primitive compared to the sophistication that the following speakers will have. I just want to say thank you, Tom, for making this possible.
Well, thank you.
So first of all, a lot of what I say will be related to the data, although I try to connect them with some theoretical ideas. And over time, I have worked with the wind tunnel data, and I've given you the Reynolds number range, direct numerical simulations, atmospheric data. Um, if you look at the real Reynolds number for these, for the atmospheric flow, for instance, it's all the order of 10 to the power 7. And the others correspondingly vary from low to high. This range, I believe, is adequate to answer questions about finite Reynolds number effects, which seem to crop up every so often. People say, well, what one observes or what you observe is really because the Reynolds numbers are not high enough. I don't know if that's the case, but I think the Reynolds number range is high enough that we can probably consider many of the measured properties as genuine. Unfortunately, different data have different limitations. I should point that out right away. But the most detailed ones are the numerical data obtained in periodic boxes using spectral methods with grid resolutions that are better than the Kolmogorov scale sometimes. In other words, they contain all the scales of motion that are of interest to us. And in numerical simulations, you can ask anything and you can compute anything you like. The people who really did the computations, most of what I'm going to talk about is P.K. Young, Diego Donzis, Jörg Schumacher, and our common students and postdocs, some of whom I will name as we go along. So this is something to keep in mind. I am always very hesitant to make statements that go beyond what the data suggests. Here is the periodic box data. So there's a periodic box in which you have a fluid with a certain viscosity, and what one does, excuse me, the largest box is 16384, although very little data from this computation has been really used. This box size is typically about 5 times the large scale in the flow. And the first few wave numbers are forced in all these data. And there are different forcing schemes that you can use. You can keep them stationary, you can have them varying stochastically, you can make them fast, you can make them slow, etc. One of the things we have recently learned is that if the forcing is very fast, then the so-called cascades about which we all know just do not exist. That is, there is a um, direct link between the large and small scales. But if it is slow, which can be characterized much better than I'm saying, if the forcing is slow, then you expect or you see cascades where the energy goes from one wave number shell to another. So, but that's an aside. But those are the data I will mostly use today. Now, just want to remind you that long before critical scaling became established, which I have written down at the top, at least in the Western world, it was introduced in 1965. But Kolmogorov really had essentially similar things, where the square of the velocity that is relevant to us, the first line here, scales with the flux of energy across scales, and this is the scale size, to the power 2/3 and some unknown function of r or eta, where eta is the smallest scale, so to speak. This is the Kolmogorov scale. And the correlation function would take this form. And the velocity, to be specific, this velocity is simply written down here as the square of the velocity difference across an interval r. If I know that these are true, then I can compute anything I want in the inertial range, certainly. And the question has been whether there is that kind of universality in turbulence. And it is asked in a more general form. Instead of the square of the velocity, you just sort of take the pth power and just extending this argument in the range where the g of r or eta just becomes unity, because the thing here takes a large value in the inertial range. It is simply um, equal to r eta to the power p by 3. What I call IR is the inertial range, R very much larger than eta, with one result that is known to be true, and that is when p is 3, it has this form. Asymptotically, that is the correct result. Now, it's now known for quite some time that the scaling doesn't follow this. I will say a little bit more about this, but it goes like some zeta p, which is not equal to p thirds. And this means that each moment, since there is no relation between one zeta p and another, each moment has to be um, explored on its own merits. And this makes the problem infinitely more complicated than traditional critical scaling. Now, there are also some caveats related to all this, which is related to small scale isotropy, whether or not the large scale is isotropic, and the finiteness of dissipation even as the viscosity tends to zero. But these I will keep in reserve just in case we want to discuss them, but I will not dwell on that. I have talked about this before a number of times. Now, so what I first want to do is to look at this function, g of r or eta. Not exactly that, but it's Fourier transform, if I might say, and want to see if this scaling is true. So in fact, this is a well-known diagram in the literature where many experiments have been plotted here. And this is spectral density, which is the Fourier transform of the G here. And here is k eta. And if everything is right, then for large k eta, or in this region here, it's not large, but it is in the dissipative range, everything must collapse. In fact, this was supposed to be a very important result. In fact, it seems to say that everything collapses, except that if you look closely, because this ordinate is so compressed, then there is usually an order of magnitude difference between one data set and another data set for the same k times eta. In fact, this is from the cover of the book by Monin and Aglow, which is the same thing with some kind of indication on the error bars. As you can see, this just keeps increasing as you go further. Now, this notice that this is only for k eta equal to 1. No experiment, almost no experiment has gone beyond 1. So in fact, if you want to stretch this a little further into the small scale beyond that, this is what you find, that there are increasing departures from this universal scaling, or if you take the derivative of that, that's the way it is. The data I showed you previously stop around here, but then you go into even deeper in the dissipative range. Instead of them collapsing better, they seem to diverge for different Reynolds numbers. So that's a puzzle. In fact, the only way I can see how to collapse them all, um, whose rationale I will momentarily explain, is instead of k eta, I will try to collapse them on k eta times r lambda to the power minus half, where r lambda is the Reynolds number. And I will explain to you why I choose minus half. If I do that, all the data for different Reynolds numbers have this exponential form, and I can get the fit for this slope, and that's the way I get them as a function of Reynolds number. Initially, beta changes with Reynolds number, but with higher Reynolds number, it seems to settle down. So essentially, for high Reynolds numbers, I claim that this form is the one that is correct and that is supported by the data. And now all I have to tell you is, instead of k eta, which is what Kolmogorov mentioned, I should really do this normalization. It's not the eta that matters for very large tails, but eta times Reynolds number to the power minus half. Okay, now where does this minus half come from? So I will explain a little bit of the argument from this paper. In fact, this is inspired by the work that Sasha Palikov did for Berger's equation. Basically, the idea is that if you look at the energy dissipation, which is the flux of energy when it comes down to the very small scales, and you take a one-dimensional cut through the dissipation field, it's not a slowly varying quantity or anything that oscillates very smoothly, but it has these highly intermittent character. There are regions where there's hardly any activity, and the regions where the activity is very large. In fact, if you take the same signal at much higher Reynolds numbers, several thousand times the mean value is possible. In this plot, it's only a few hundred times the mean value. Charles and I spent some good part of our time trying to figure out the multifractal characteristics of this and things of that sort. But the point I am making is that if you remember the definition of the Kolmogorov scale, it has the dissipation in its definition, and the dissipation is locally highly varying quantity. Therefore, the dissipation scale, instead of being one number for a flow and one number for a flow at a given Reynolds number, it is actually a varying quantity, or you might say it's a field in the general vocabulary. Therefore, if in fact there is something like a cascade, the cascade doesn't just go uniformly and stop at some uniform scale at all places, at all positions in space, but it has a local nature. It will truncate at different scales at different places. Now, if you are looking at the velocity difference, which is the quantity of interest here, you can push it all the way to eta, which is the scale that is a crossover between the analytic dissipation region and the singular region for the inertial range. Now, let's assume you can do that. And then the definition of eta would be that the Reynolds number based on this velocity increment across eta and eta itself, that's what I've written down here, eta times There's a length scale, there's a velocity scale divided by viscosity is 1. That's a definition for eta. This is the definition that Kolmogorov himself used for uniform eta, but we can sort of say that this would be true locally. Therefore, the eta, which is now not a given number, but a field, as I said, eta is nu divided by the velocity increment across this eta. Now, if you accept that, you can always just get all the velocity derivatives in this fashion. For u, you put in delta eta u, and d by dx goes like 1 over eta. And using this relation, you can write it like that. Now this is how you can do any derivative you want. Now, if you are interested in the mth order moment of the velocity increment, which we think is going like r to the power zeta m, these are the anomalous exponents, then from the equations you can write down for s to n without any approximation and so on. With one caveat that I will mention, you can get the relation that the 2nth order moment is related to the 2n plus 1th order moment in this fashion. And then using this kind of relation a couple of times, one for the crossover scale for the 2nth moment, which will be different. The crossover scale will depend on the order of the moment. So for the 2nth moment, and once for pushing it all the way to L, you will get this relation. Eta 2n, that is the crossover scale for the 2nth order moment divided by the integral scale, large scale, is Reynolds number to the power this quantity. 1 over zeta 2n minus zeta 2n plus 1 minus 1. If I let 2n go to infinity, or n go to infinity, which is really very large order structure functions. Now, and if I say that for large order, these structure function exponents in the inertial range saturate, which I will show you momentarily, then it's clear that zeta 2n is the same as zeta 2n plus 1. And I have the relation that eta 2n for large 2n becomes Reynolds number to the power minus 1, which is Kolmogorov scale raised to the power times Reynolds number to the power minus quarter, or Reynolds number microscale Reynolds number to the power minus half. So that is the smallest scale that is in the flow is not really the Kolmogorov scale, but this eta infinity, or in the quantity when n tends to infinity. And that's the quantity that I use. That is, the tails are not really to be thought of as universal in terms of the Kolmogorov scale, but scales that are finer and depend on the Reynolds number. So that's where we have, and I think the fact that this saturates here, this exponent, is an indication that it probably works. But I will mention this over and over again, especially considering the saturation of exponents. Now, when we looked at these tails of the spectrum, you can see that in this case, it has gone up to k eta Reynolds number to the minus half of 7 or so. That means actually for this Reynolds number, something like k eta of 10, 1/10 of the Kolmogorov scale. Of course, you can keep going lower and lower. And the question is, which is the question that Greg Ink asked, and he probably will ask today as well. At what point should we be worried about thermal noise? Clearly, there's thermal noise. And so as the scales become smaller and smaller, shouldn't I be worried about them if I am interested in any physical flow? My answer could be two different types. One is the Navier-Stokes equations are important in their own right, and I don't care about thermal noise. So the question is still worth answering as an issue related to the equations. But the problem then may become more academic if the answer is in fact correct. This question was asked for the first time, I heard it in 1978 when I was at a conference. So I sat down and worked out this relation. Um, and that is Kolmogorov scale to the mean free path, which is an indication of when the thermal fluctuations become important, can be written down as Reynolds number to the power quarter divided with the Mach number, which is the ratio of the flow velocity to the speed of sound. And I was happy to see that this issue was addressed in 2006 by Bob Moser, who got the same result, obviously. And this number here depends on the flow and the which material it is that is flowing. For air, it's of the order 10, something like that. Now, the Mach number cannot be very large. If it is beyond about zero point 0.3, compressible effects start coming in, and it's a different problem. Suppose that the minimum Mach number beyond which compressibility manifests also varies with respect to Reynolds number, say Re to the power m, where m is positive and small. I don't know that this is exactly true, but the minimum available data from Diego Donzi's simulation seems to suggest that that may be the case. Then I have the Kolmogorov scale divided by the mean free path is Reynolds number to the quarter plus some m. If this is true, then this ratio is never unity. Um, um, I never gets to be unity for any finite Reynolds number, large Reynolds number particularly. So I don't need to really worry about this point of thermal noise at all. On the other hand, if I say that it's not the smallest scale, eta is not the smallest scale, but it is replaced by the eta minimum that I already computed for you, which is this eta times Reynolds number to the power quarter, then I have this result. Eta minimum divided by the mean free path is A times Re to the power m, where m is some small positive number. And I don't know too much about it. Therefore, I'm really not sure whether it exists or not. So if in fact m is 0, then it says that the minimum length scale in the flow, which is appropriate to the very highest order structure functions, then basically I have to worry about the thermal noise somehow, and the Navier-Stokes equations may in fact be affected by it, and I have to worry about it. But just remember that this eta minimum is the very end of the tail end of the spectrum, beyond which there is nothing, so to speak. And if you put in any finite Reynolds numbers, you can actually work out what that ratio is, this ratio. It's still, it's not unity, but it is a relatively large number, say of the order 10. But of the order 10, you really have to worry about such things. So I will leave this as a opener for Greg Ing to talk more about. So that's one point. And the other point I mentioned here that the inertial range exponents may saturate or not. Well, let's see if they saturate. So this is in this paper. Normally, people have measured the so-called longitudinal structure functions. That is, the direction of u and the direction of r is the same. On the other hand, if you take the direction of the separation distance perpendicular to the velocity or vice versa, and you want to compute the exponents corresponding to that, this is what you find as a function of the r or the moment. Now, this is the Kolmogorov value, which is p by 3. And these are the data that are known from previous measurements, including ours, for the so-called longitudinal structure functions, which deviate from Kolmogorov, but they do not show any signs of saturation. And these lines are various models about which I do not want to dwell. If, on the other hand, I take these so-called transverse structure functions, where the velocity difference is across the separation distance, then they clearly saturate. They do saturate here, and the saturated value that is around 2.6 or something like that. It's not very far from 2. And we speculated that, in fact, this is basically um, kind of vortex sheets which are just torn off into pieces sometimes and punctured through very large scale fluctuations. But basically, it is highly perturbed vortex sheets, which Sasha will probably talk a fair bit about. So that was the speculation. That part was speculation, and you can take it or leave it. So this is the indication for the saturation of exponents. And after we saw that, oh, by the way, one part of discomfort in all of this is that even at the highest Reynolds number we have considered, which is really very large, because remember, the large scale Reynolds number is proportional to the square of this. The scaling range is not very, very large. There is a very clear indication that there is scaling. And as you increase the Reynolds number, this range increases, but it is not many orders of magnitude over which I can fit the power laws or straight lines on these local slopes. These are just local slopes, which should show extensive horizontal lines if in fact there was extensive scaling. Now, this is the caveat you have to remember, and the extent of this scaling region does increase with Reynolds number, but not anywhere as fast as the classical argument might suggest. So there is something there that I have thought about, but I will not dwell on today. But let's take it for what it is, and those are the data that I've just shown. Now, another indication that there is a saturation is that if I take the probability density, and if the high order moments saturate, that is the tails of the distribution have somehow become saturated, then if the saturation exponent is a zeta infinity, let's say transverse, if I normalize the probability density in this fashion, then they should collapse towards the tails. And indeed, they do extremely well for two Reynolds numbers that I have shown here. So everything points to the right conclusion in this. Now, after we saw this thing, I just asked Karthik, who really did these calculations. Let's push it. Let's push it to much higher order. Any sane person would stop around here, which is where I had shown in my previous graph. So we used all the data available, and just to the consternation of PK Young, we just used more and more computer time. And even the longitudinal ones seem to saturate for very large orders. Whether you believe it or not I can only say that as a matter of convergence of the data, they do actually collapse. There is no issue with respect to convergence. There may be other issues that the data have that I cannot address at the moment. But the point is that it saturates probably around 3.5 or something like that. I'm not sure what that number means. There is absolutely nothing that prevents it from taking on any value it chooses. Basically, what this means is that suppose I think of vortex sheets, and I am looking at the structure functions of velocity difference across the vortex sheet. Then they saturate earlier, and they saturate around 2 or something, 2.5 or something like that. But if I'm taking longitudinal ones, that is along the vortex sheet, for instance, then it assumes a higher saturation value, and that's where we are. And all these models that people have made in the past do not take into account any possibility of saturation at all. So that's the new part. So I ask the question, which people here will have some opinions. We have known for some time that turbulence has anomalous scaling. This is not new, and over and over, and me particularly, we measured it many times in many different ways, many different flows, and I think that is the case. Even if the caveats that are associated with it are violated modestly, that is, there is small anisotropy, etc., they appear to be universal. I should put in a quotation marks around universal, but they are to the measurable accuracy the same. But if you have very strong shear or something like that, then it's a different ballgame. So that's why I said violated modestly, they appear to be universal. But the new aspects are different components scale differently. So if I have a phenomenon whose structure functions in one direction as opposed to another scale differently, should I be worried about what it means to say that the problem is scaling at all? And also the fact that they saturate and saturate at different levels. What does it say about scaling? Initially, it was thought everything is homograph. Then we thought, well, it is anomalous. It took a long time to establish that. Now, new features are that different components scale differently, which is something that we had known from before as well, but now much more definitively. And then the fact that they saturate, I don't know what it all means for scaling. So I will leave it for later discussion. Here is a bigger table which says about various things, but I will not dwell on it in view of time. Now, I want to talk a little bit about the next topic, which is the topic of Sasha Migdal. This is Euler loops in 3D turbulence. There's a considerable work on Lagrangian loops, Peter Constantine and the others. I will not talk about them at all. So I have a loop circumscribing an area A, and I just calculate this line integral around the loop, which by Stokes theorem is just omega dot n, where omega is the vorticity, which is the curl of the velocity field. Now r could be square root of a if a is a circle or a square, but it could be something different with a prefactor that is different for different types of loops. Now, the literature on this is very small. Sasha Migdal in 94 wrote this paper, 94 and 95. And I was working on wakes at the time. And very soon after, we started making measurements in wakes and also in numerical simulations. And Umeki, who did the work in 1993, was actually inspired by Sasha Migdal. No, but we were not very conclusive at the time because the Reynolds number that was available to us was relatively small. So recently, using these huge databases we have, we wrote these two papers up to box of 8,190 cube, and I will tell you results from that. And of course, Sasha, as you know, really got interested in this, and he has written several papers, which are all on archive, and I'm sure there are more. So now he will talk a little bit about what his latest findings are, but I want to give a general background. One of the points of Sasha Migdal's theory is that there is the so-called area rule, which is to say that if I take a loop, and as long as the area that it circumscribes is the same, independent of the shape of the contour, the circulation statistics are the same. Of course, I can't test it in its great generality. And what I'm going to say is in these two papers. But let's take loops which are like rectangles of different aspect ratios. Now, we take different loops circumscribing the same area that is given here, which is in the very well in the inertial range. As you see, it's a many fold compared to the smaller scale. And you can keep the area the same, but then change L1 and L2, which are the sides of the loop. And you calculate the probability density of the circulation and plot it against the circulation itself. And you see different symbols, which are 5 here for 5 different contours. They're all plotting along each other uh, pretty well, except for these tails, where we have a very small number of samples. So let me say I discard them for now, simply because I have a very small number of samples. And the red lines here are this fit exponential lambda c divided by square root of gamma c. This is the fit that Sasha Migdal got from his theory, which he will tell you. And in fact, there is slight asymmetry between these two, and the asymmetry is primarily in this region, but towards the tails, both tails are fitted pretty well by this formula. And as I said, these are all the data, and you should not worry about convergence and things like that. And I certainly will not tell you things that have such issues. What is plotted in the inset here is for the Gaussian noise with the same correlation function as measured. Um, and again, of course, you can see that they all collapse, but the shape of the distribution is very different. And this is essentially a Gaussian. Now, however, even though they seem to all collapse, again, I make the same point that this ordinate here is so crunched that you might not be able to see the differences and see if there are any systematic ones. And Sasha Palikov, last time I spoke about it very briefly at the Institute, he was there, and he later on sent me a note. Suppose I write gamma c squared, that is the circulation, in terms of the correlation function, which is easy to write. And in the inertial range, we let's say it follows the second order structure function that we know about which I spoke generally. And then you can compute this whole thing, which turns out then a certain number sitting in front times r to the power zeta 2, where r is the linear dimension of this contour C. And that's perfectly fine. But the prefactor that you compute from all this depends on the shape of the loop, whether it is a square or a rectangle with different aspect ratios. So in fact, his point, as I understood it then and understand now, leads to the perimeter dependence of gamma c squared average. So the area rule cannot strictly hold. Now, of course, Sasha Migdal has gone back and forth on this a little bit, but now we understand from many things what I'm going to say, which is that if I restrict myself to the inertial range, which is what we should be concerned about, and compute this quantity here, the second order moment, say one half of that, for loops of different aspect ratio and normalize it by the same quantity for a square of the same area. Now, if in fact area rule were to hold precisely, then this quantity must be independent of the contour shape, or as I have plotted here, this is just the indication of how stretched out the contour is instead of being a square. Now, when L1 is equal to L2, that is a square, this number is 4. And our inertial range extends up to 4.6 or so. And this is the quantity plotted here. As I said, if it were perfectly true, it would be here. But otherwise, it is along here for second order. Fourth order is here, sixth order, eighth order, 10th order, etc. The higher the order of the moment, the stronger it departs from this thing here. But there is one thing to note, and that is the departure is initially very large in going from 2 to 4, but this departure becomes smaller and smaller as you go to higher and higher order moments. That is to say, something happens at very high order moments which sort of saturates and doesn't move anymore. And in fact, this dashed line is here from Sasha Palikov's expression that is computed from the previous transparency. Now, what I'm going to show you next is how fast things change from here to here, from here to here, et cetera, yeah, as a logarithmic derivative difference. And this is for the second moment, fourth, sixth, eighth, and 4, 6, 8, 10, and 12. And this is the inertial range, where here there is some variation, but for large order moments, essentially there is no change whatsoever. And I will show you what this line is in just a moment. So in fact, for high order moments, there is a certain universality, and we can explain that a little bit better. Now, remember the fit that Sasha Migdal got, and for the circulation, probability density of the circulation. So use that expression to compute this gamma c to the power m average value, and it's here. And it just is some number here which depends upon the two coefficients in the fit times the gamma function. This gamma is not to be confused with this gamma. Now, for large M, you can do asymptotics, and you can show that this logarithmic quantity, something I had plotted before in the previous plot, this thing here, is simply asymptotically dependent only on M and N. There is absolutely nothing else in this expression. So this ratio is independent of the loop area, is independent of the prefactors alpha and B in the PDF fits, and only on the order of the moment, the difference from M to N. So in that sense, the tails of the PDF are universal, and I will discuss this further in Sasha's presentation. So now there is another interesting thing. Instead of taking just a simple loop, suppose I have a figure-8 loop like this. If I go along here and use the notation that the area to my right is positive, it's positive, this is positive, but if I go here, it is negative. So when I'm computing the area around the circulation around this area, should I just take this area to be positive or negative in relation to this? In other words, should the area be summed up algebraically or simply arithmetically? Now, there's a big consequence to this, but if I simply say, let me just add them up without worrying about the signs, then the second order moment goes like L1 squared plus L2 squared to the power 2/3, L1 and L2 being the numbers shown there. If on the other hand, I take the vector sum, then it goes like area to the power 1/3, which is a very different thing. So you actually compute it. This is what you find. It goes like 2/3. And well, that shows that the scalar area rule is correct. And in fact, these symbols here are for different contours, and they look all plotting on top of each other. As we did already, if you expanded this, there's a systematic difference in going from one to the other. But if you take very large order, which we haven't done in this case, presumably that will not be the case. Now let's do another thing, and that is let's take the contour not on a plane like we have done before, but in 3 dimensions. So I want my contour is like this. And Sacha was the one who said, well, the minimal area is what matters, and minimal area is not either the projected area in one or the other direction, or just the not just the sum of that area plus sum of this area. Now think of it as the soap film that extends from here to here, but it touches these edges as well. So you can do this. You can calculate the circulation around this minimal the contour for the minimal area, and you can also ask yourself whether the circulation properties are the same as the circulation properties of an equivalent planar area. So you can have a planar area here, which I've depicted, to have the same area as this minimal surface. Now you can do the computations, and you can plot here the probability density of the circulation as a function of the circulation itself. And what you find is the open circle are for the planar areas, and these red ones are for the non-planar. In fact, they don't agree. They don't agree in these absolute units. But if I normalized it by its own standard deviation, as we have done here, they collapse up to let's say 10 standard deviations. And there are differences here. As I said, I don't know how much I should trust, but essentially there is a uh, agreement over a significant part to emphasize the positive aspects. And you do the same for the Gaussian noise. That's what you find there too. You find differences. Now let's take all these caveats in our back pocket and just compute the scaling exponents for square loops, assuming area rule works, and therefore square loops is the same as rectangular loops, same as whatever else. Now this quantity here, peak moment of the circulation around contours of size r to the power lambda p, and if there is scaling, these things should be straight. And instead of drawing lines here, what I've done is to take the local slopes of these and plotted here. For second order, this is here. For fourth order, it is here. Sixth order, eighth order. This is supposedly the scaling range. And in fact, you can see that even at the high order, it seems to scale pretty well. And these lines here are the Kolmogorov scaling. And you can see as you increase the R to the moment, the scaling decreases, departs from the Kolmogorovs more and more and more. And um, you can actually plot those scaling exponents as a function of the R to the moment. And this is the Kolmogorov line. And these are the data, and the data lie on the Kolmogorov line until maybe some fourth order, something like that. And then it starts to depart. And the nice thing is they seem to plot on one line rather than on a concave curve that really is the essence of multifractality. Now, actually, it seems to plot exactly on the Kolmogorov line here, but if you expand it, you can see that there is a definite but small deviation. I don't know whether it's real or not at the moment, but let's say um, that is. Now, this is the departure from Kolmogorov is plotted divided by what should be Kolmogorov as a function of the order of the moment. This is for the structure functions, and this is for the circulation. It departs from Kolmogorov, but by a significantly smaller amount than for the structure functions. I'll come back to this curve in a minute. So if I take this lambda p divided by p, we did this because in Sasha's theory, at least one version of it that I know, this number is just a constant. Now, the data do not show that that is the case, but it may very well be that I have to go to high order moments and then it may become a constant. And the point is that if it does become a constant, then there is no choice for these data um, except to lie on one straight line. In other words, perhaps if I go to higher and higher order, if I go to higher and higher Reynolds number, something like that, this region, which plots on Kolmogorov, might extend to higher and higher order P. In which case, then everything is very simply a Kolmogorov type, and maybe there are small departures, but we can handle that. Now, to understand whether it is true or not, what we did was to compute this delta P for different Reynolds number for different RPs, and we found that with increasing Reynolds number, I I did it for lower Reynolds number just because this is the highest I have and I can't go any further. What we found is that this curve, in fact, becomes more and more to lie on this line up to higher and higher order P, the more the higher the Reynolds number. In other words, it's conceivable that something like this might in fact shift to this line up to some higher P and thereafter depart a little bit less, etc. Okay, that's partly based on data and partly on speculations. So now I must stop pretty soon. So some comments and questions. The universal form proposed by Kolmogorov does not work. I mean, it's not disrespectful of Kolmogorov or anything like that, but it does not work. But it continues to be inspirational to us. I mean, there are always issues relating to whether, well, if I went to tenfold higher in Reynolds number, would it make a difference? But now we have done it at several Reynolds numbers, and if Reynolds number is the only criterion, it doesn't look like that is a significant factor. Scaling is much richer than what you find in critical phenomena, where if you tell me the correlation scale or one other scale, everything is related to each other. And that would be true, perfectly true for the standard colmograph. But now they are anomalous. And as I said, they saturate, and then different components scale differently. The saturation simply means that at very high orders, it basically you've reached a stage where neighboring fluctuations could in fact be of the order of the large scale velocity itself. So in other words, it's becoming something like a shock, something like burgers. And this certainly is more true for transverse quantities than for longitudinal quantities. If you look at why the three-dimensional Navier-Stokes differs from three-dimensional burgers, of course, pressure is the most important thing. And it is known for some years now already from the work we did that the pressure effects are smaller for the transverse structure functions than for longitudinal. So everything hangs together in my head. Now, in other words, scaling problem is much richer than it is in standard critical phenomena. Now, the circulation is quite promising as an alternative, if you like. Well, some 80 years down the road, it's about time we actually started looking at some other things. Some questions to answer are, the area rule is good for the tails, but not necessarily for the rest of it. Although as a reasonable approximation, it seems to work for essentially the entire PDF. For an increasingly higher Reynolds number, it seems to become universal, the PDF tails. And do they eventually become Kolmogorov-like? In other words, some straight line in the plot of structure functions is a function of the order of the structure function. It doesn't have to be exactly 1/3. So those are the types of questions that occur to me that we could discuss. With this, I am signing off, and we have a little time for discussion.
I wanted to add a small comment. Do you hear me?
Yeah, I do.
The comment is, I'm sorry for so many papers, which was kind of development of the same theory, but what I converged to is the prediction that the shape of the distribution, which is exponential times 1/squared of gamma, is indeed universal. The coefficient in front indeed could depend on the shape, because when I did those preliminary results based on loop equations, I didn't see that. But now that I see with vortex dynamics, which I'm going to talk about, I see much more detailed equations. And from them, I only see universal shape of the curve, but not coefficient. So I no longer argue that all these area laws are only, at all scale. It's only for high moments, because high moments correspond to the tails of PDF. So I have only these predictions for the tails of PDF, because that is the asymptotic WKB prediction, where I can make something.
I will add a little bit more actually. If you take whatever the coefficients are, if I computed the logarithm of the difference in slopes, that basically is a number that does not depend on the coefficients in your fit. They simply depend on the order of the moment. So I think it's quite a bit more powerful than you very generously mentioned.
Well, I only say things about asymptotics. Maybe it is valid in a wider range than I expect.
Yeah. Thank you. Yeah. Okay.
Can I ask a question?
Yes.
Two questions. Well, one question, in the slide where you had the distribution of the circulations, we're just talking about the gamma divided by U prime L,
Yes.
capital L.
Yeah.
What capital L was that?
Is the integral scale. There was just
that-
a way
okay,
to
okay.
normalize that did not have
Sure,
any
sure.
viscosity in it.
Sure. Okay. Yeah, I wasn't sure. The other thing is the length scale, the eta divided by r lambda square root
Yeah.
that you identified.
Yeah.
There, if I did the little algebra right, that turns out to be nu over u, where u is the velocity scale in your in your r lambda.
Yeah.
And that when I see nu over u, I think about the inner boundary layer length scale in
Yes.
shear flows, the inner
Yes.
length
Yes.
scale,
Yes.
and so on. And
also shocks.
in some sense, it's
exactly. So it's the
Yeah,
same type of singularity, I think.
yeah, that's interesting.
Yeah.
So in some sense, for a fixed capital U, it's independent of eta. So it really so that scale you proposed is in some sense not dependent upon the flux. You see, it's just nu over u.
Yeah.
Well, of course, u depends upon what.
Now that of course does not mean that the inertial range is controlled by these things, but these very fine scales seem to be controlled by this length scale.
Yeah, it's interesting because and the u you use there, the u prime that you use there is just the integral velocity scale.
Yeah, root mean square to be.
Yeah.
Yeah.
So these are all. So that small scale then is written very simply in terms of the viscosity and the large scale velocity.
Absolutely right. I did make
That's
that
mysterious.
remark, but wasn't very clear. What I said was that we will reach a stage where across these very fine scales, the fluctuations almost are the large scale velocity.
Yeah.
That's what it is. Yeah.
Mm.
So somewhere the very high order moments are controlled by these very large fluctuations, and you must have them if you have pressureless effects somehow, and that's what it will amount to.
It's amusing to know that this eta dependence, I mean the smaller scale depending like nu, is also the Kato scale. So that's a scale, there is a smaller than Kolmogorov scale over which the transition to anomalous, so the non-Euler limit can survive in the presence of boundaries. Okay, so that's predicted by some calculations of Kato.
I also saw this number long ago in your paper with Fias in the Journal of Fluid Mechanics. I think you calculated the attractor dimension and you came up with the number Reynolds number to the power 1 rather than 3/4. And I think that is related to this, as I understand.
Yeah, but I mean, those are just limitations. I think that maybe they're the same kind of limitations, meaning that the theorem by Kato is in one direction. The direction is that if you control everything below this, then you're going to be okay.
Yeah.
The mystery is there's supposed to be no boundary layers in these. There's no boundaries in these simulations.
Boundary is to be taken, I would say, metaphorically. Yeah.
Hi, Srini. This is Sladik speaking from Prague.
Hi, Sladik. How are you?
Thank you. I would like to ask one question. If you remember, years ago, we measured temperature structure functions in convection. And it seemed to me that these scaling exponents, they actually saturated much earlier than just what you have shown here. So my question is how the passive scalar and what you have been talking about is related, and if you can comment on that.
If I can share my screen one more time, assuming I find it. Yeah, okay. In one of the okay, let's I don't want to do all this. Sorry. Okay. You see the crosses, Ladik? The
Yeah.
crosses are in fact for the passive scalar. They, of course, without any ambiguity at all, saturate. And they saturate much faster. I didn't mention this. It's very similar to Burgers or Craignon model. And it saturates at a value like 1.3 or something like that. And this can be related to the fractal dimension of these structures, etc., which we did. And notice that basically it starts to depart from the Kolmogorov value even from second order. And I do not recall how it compares what we found. I should plot on the same graph. Yeah, but your observation is entirely correct.
Thank you.
I wanted to make one small comment about physical meaning of your remarkable exponential distribution of circulation. Maybe it's worth noting, circulation is, in fact, integral of vorticity over the surface. So it's sum of large number of vorticities all over the surface inside the loop. Now, if those would be like random variables, if you sum large number of random variables, you will get the Gaussian distribution by central limit theorem. The only exception from central limit theorem is the situation when these variables are strongly correlated. So your strong violation of Gaussian distribution, and in fact, you have exponential distribution for like 6 decades, strongly indicates that there are coherent structures.
Yeah.
There are coherent vortex structures. And that's the point of my future talk, which I will talk today, is that not only we experimentally see those vortex structures, we also see that indirectly from the experiment simulations of Srini.
Yeah, Sasha, thank you very much for that. And that's the reason we went to do the same calculations for random Gaussian noise. And we found that it's Gaussian, as you just said, instead of being exponential of the sort we find for the circulation. And that was mainly the purpose of those calculations. Yeah, you're right. Yeah. Tom?
Yeah, I was wondering whether at a mathematical level, one has any chance of understanding the saturation in passive scalar. Is that, I mean, can you understand the mechanism intuitively there?
The same mechanism that is there for Burgers, I would say.
Okay. Well, Burgers is fairly clear, right?
Yeah,
Because
so this, I would
because of
say
soft.
by analogy, it is also very clear to me. I mean, but mathematically, I don't know.
Yeah.
The thing is, when you have temperature signals, they display the very clearly the ramp cliff structure. That is,
Mhm.
temperature increases very fast and then slowly decreases. And if you have a coherent structure, at the front of it, you have a boundary layer, very thin boundary layer across which the jump takes place. And slowly in behind the structure, it sort of comes back to the ground. So it is essentially things going up very slowly, coming down very fast, or going up very fast, coming down very slowly. And it is a direct influence of this. And that's what you find shocks in Burgers. So I think they're all the same. So I think it makes me very happy in some ways to be able to think about all this in a more general way. But I don't know, I can't even tell you if you put in front of me a mathematical proof, whether I can tell you it is a proof or not.
Yeah.
So I don't